In this presentation, let's take a look at canonical form. First, let's take a look at min-terms. Min-terms are otherwise known as standard products. They represent the possible AND combinations of n variables. Given that you have n variables, you have 2 to the n possible AND combinations. The example shown on the screen uses 2 variables a and b and the corresponding 4 combinations for ANDing those 2 variables together. Note the min-terms are identified by the 2 variables, either primed or unprimed, and by the lowercase letter m with a subscript indicating which min-term, starting at 0. Max terms, otherwise known as standard sums, are the possible OR combinations of n variables. Here we see a similar example to the previous slide, though max terms are now identified with an uppercase M, though again it uses a numeric subscript starting at 0. Given a truth table, any function can be put into algebraic form by ORing together all of the min-terms that have a 1 in the result column. In the example shown here on the screen, 2 rows, the row for min-term 1 and min-term 2, have a 1 in the result columns. By ORing together these min-terms, we arrive at the function defined in algebraic form. It's important to note that any Boolean function can be expressed in this way. Similarly, given a truth table, a function can be put into algebraic form by ANDing all of the max terms that have a 0 in the result column. In the example you see here, we see that by taking the max terms m sub 0 and m sub 3 and ANDing them together, we arrive at the function definition in product of sums form. It's important to remember that any Boolean function can be expressed in this way. So canonical form means that Boolean functions can be expressed algebraically as either a sum of min-terms or a product of max terms. Complements come in handy with canonical form. The complement for a sum of min-terms is simply the sum of min-terms that are missing from the original function. The example shown here for 2 variables and 4 min-terms uses summation notation, which is often a shorthand for expressing a function algebraically. Converting to a product of max terms also involves the use of a complement. Remember that any min-term is the complement of its corresponding max term. That's an important fact that we'll revisit again in the future. What this means is, if you start off with a function defined algebraically as the sum of the 2 min-terms 0 and 2, taking the complement of this gives you the summation of the min-terms 1 and 3, the 2 that were missing from the original function expression. If you again take the complement, or the complement of the complement, you arrive at a product of max terms, specifically the product of the max terms 1 and 3. In this final example, we look at a function involving 3 variables. If we wish to express the function as a sum of min-terms, we look for those min-terms, or those rows, which have a 1 in the result column. This leads us to the summation of the min-terms 1, 4, and 5. Alternatively, if we wish to express the function as a product of max terms, we look for those rows which have a 0 in the result column. This leads us to the product of the max terms 0, 2, 3, 6, and 7. Notice that these numbers 0, 2, 3, 6, and 7 are the rows that did not appear in the sum of min-terms.